Hi, I'm Sina and I'm presenting for Numbers 2021. Here we have in gray the share of population of each ethnic group in Chicago, and in orange we have their share of COVID cases. As we can see, for the Hispanic and Black populations, which have been historically of lower socioeconomic status, they have been disproportionately affected by COVID. Uh, we actually see the opposite effect for the white population. And this is not just something specific to Chicago, as it has been well documented that income inequality and lower socioeconomic status leads to a higher infection probability. So it all comes down to this message. We are not all in this together. We devise a model to investigate how your socioeconomic status and your capability of quarantine can affect your infection chances. So in our model, agents have two options: quarantine themselves or go out and work. In each situation, individuals receive a negative reward, which is actually punishment. In case they stay at home, they will lose some of their income, and in case they go out, they have this fear of getting infected, and that fear is proportional to the number of active cases at that moment in the population. The probabilities that we attribute to the choices are based on this exponential form, which is actually an established form in game theory. So Ri here is the punishment that individuals of the socioeconomic group I receive in case they stay at home, and Rd is how frightening the disease is for the population. I is also the proportion of the infected agents at that specific time in the population. And beta can be thought of as this parameter indicating the intensity of selection. When beta is very low, near to zero, individuals do not have preference between the choices, regardless of their reward and punishments. And as we increase the beta and we go to infinity, individuals will most likely choose the option which has even a slight advantage over the other option. So our spreading model here is based on a SIR model. Different symbols indicate different socioeconomic groups, and colors indicate their status regarding to the disease. So we start with one infectious agent, and they can transmit the disease to their neighbors, but there's also this quarantining scheme. So here this square has quarantined themselves, and by doing this they have deactivated all of their connections to their neighbors, so they can neither get the disease or nor transmit the disease to their other neighbors. And eventually, we have this recovery state, and agents can recover and they will be immune to the infection for the rest of the time of the simulation. Our network model is based on a stochastic block model network. A stochastic block model is a generalization of an Erdős-Rényi model. So individuals of two different socioeconomic groups or blocks have probability rho ij of being connected to each other, and this matrix here indicates the probability of being connected between two different socioeconomic groups or blocks in the language of a stochastic block model. This is a fully segregated situation. Only the values on the diameter are above zero. Here we have a fully homogeneous situation, and people do not discriminate. By constructing a linear combination of these two, we arrive at the probability matrices that we construct our networks based on. So this S here is the intensity of segregation, and it varies between 0 and 1. So the last part of our model is the punishment that individuals receive if they stay home based on their socioeconomic status. So for the wealth distribution, we use this Pareto distribution, and this lambda here is a parameter of Pareto distribution, and as we increase lambda, we get to a more equal situation of wealth share. So here we have divided the population into 10 different deciles from poorest to the richest, and we have the share of wealth of each decile for two different values of lambda. And we know that actually rich people are punished less by losing their income. So the value of the punishment should be 1 over their wealth. So in addition to our probabilistic agent-based model, we construct this analytical model based on the mean field approximation, so we can better mathematically study our model. So as for our results, here the y-axis is the proportion of infectious agents at the time in the system, and different colors indicate different deciles or different socioeconomic groups. The dots indicate the values for the ABM model, and the lines indicate the values for the ODE model. And as we go to the bottom, we go to the higher SES groups. So what we see here, initially all of the groups increase with regards to their infection rates, but higher socioeconomic groups start quarantining as they see the number of infectious agents in the population is increasing. So they actually get scared. But the poorest populations, which do not have the luxury of quarantining themselves, they just go on to achieve herd immunity. And as their rates start dropping, the higher socioeconomic groups, they get this false sense of safety, and they start coming out of quarantine and giving rise to a second peak. So over here, instead of the time series, we work with the total infected people at the end of the simulation. So again, the colors indicate different socioeconomic groups, and the blue color here indicates the proportions for the overall population. And again, the dots indicate the ABM model, and the lines indicate the ODE model. Just because the network model is a little bit slower than the ODE model, and this is something that we expect because in the network we have loops which are non-existent in a mean field approximation. We have slightly adjusted the aspects of the two diagrams, but they actually have a very strong agreement with each other. So what we see here is that as we increase this lambda, which is an indicator of the wealth equality in the population, it is true that the infection rates for the wealthier deciles increases, but the overall population is actually benefiting from an increase in equality. So we also check the robustness of this result with respect to other parameters. So R naught here is the intensity of selection. This is actually the most famous epidemic parameter that everyone knows. So mu is the transmission probability, k is the average number of neighbors an individual has, and gamma is the recovery probability. And so the y-axis is R naught, the x-axis is lambda or equality, and the color code is again the total number of infected people at the end of the simulation. So it is not surprising as we increase the value of R naught as we go up, the number of infected people increases. But the interesting thing is that as we, for different values of R naught, as we go to the right and we increase the equality, we actually see again that drop in the rates of infections for different values of R naught. So it shows that the result is still robust. So to check the robustness again with respect to another parameter, we pick segregation, and as we said, the segregation can change between 0 and 1. So when we change segregation, it is interesting to see that the value, the number of infected cases actually increases as we move toward more segregated regimes. But it's still, even if we vary the value of segregation, still by increasing the equality, our infection rates will drop. So overall, we observed a secondary peak for higher SES groups. This was due to the fact that they achieved this false safety mindset after they saw a decrease in the infection rate. So they thought it's good to go out of quarantine now, and that led to another peak for them. On the other hand, we observed that equality benefits the society by lowering the infection rate, and on the other hand, segregation worsens the situation by increasing the infection rate. So as for our future work, in our current model, agents process the information globally, so they care about the infection rates across the network. This is something similar to watching the statistics on TV. But perhaps it's more realistic that you give more importance to your relatives and friends, and if some of them get infected, you will become more fearful, as opposed to a random person getting infected and showing up in the statistics. Um, Another thing is having a distribution of tendency to quarantine within each socioeconomic group, because people tend to think differently, and some people are less and some are more cautious about the infection regardless of their socioeconomic group. Um, it would be interesting to see how different spreading models such as SIS, SIER, they would perform on this model, and to also have other types of networks which, besides the connectivity between the communities, have some sort of small world behavior, and also clustering, and etc. So thank you very much. Looking forward to your questions.